So this is the world's first electric motor. So yes, here's the history. Since the birth of technology, the pace of innovation has continued to accelerate. New and new technologies keep making our lives easier. One of those technologies are an electric motor, which are used to power many things, like Tesla cars, or RC cars, or computer fans, electric toothbrushes, all that stuff. Well, the story of electric motor has been no exception. Following the trend of innovation for the past 200 years, looking back at the invention of the first electric motor in 1832, it's hard to imagine the impact electric motors have already made on our lives and other technologies. So yes, Hans Christian Ørsted was experimenting with electricity in 1820. But suddenly, he observed that in one of his experiments, he found out that when a compass is deflected when he held an electrified rod next to it. He had just discovered electromagnetism. Well, back at that time, he thought it wasn't going to be very useful, since electricity was never really a thing, and many people actually feared electricity as a sign of madness from the gods. So he didn't really know what he had. But it wasn't long before scientists around the world, like William Sturgeon, an English physicist, made the world's first working DC electric motor in 1832. On the right is the world's first electric motor. But the problem with the electric motor was that it still plagued some motor efficiency and gave very little power output. So it didn't really give the expected output. As a matter of fact, the input actually, if you gave 5 watts, it would only return 3 watts in power. So you were basically losing power. Well, that was still pretty impressive for that time. But this Russian guy called Moritz von Jacobi was the first electric motor to set a world record for mechanical power output in 1834. What this means is that his electric motor on the left actually gave a power output instead of the one on the right, which actually didn't give any power output, but actually wasted energy. The one on the left actually gave a power output, making it efficient and worthwhile. As a matter of fact, he was able to get 14 people across a river using a boat powered by his motor. But this was still very behind to today's electric motors. This is going to be the world's first electric motor, which actually is pretty good and has a stable power output. On the one here. So, after a number of efforts, the world's first practical motor, which is on the left, was made and improved, which is the same picture, but it was just improved version. It was made by Antonio Passotti and Belgian electric engineer Zenobi. However, only American inventor Frank Sprague is credited with inventing the world's first practical motor. Well, why they call it practical? Unlike the other electric motors at that time, this motor had a constant power output. For example, the other motors beforehand didn't have a constant power output. Sometimes it'll go higher watts, sometimes there's lower watts, which doesn't mean there's going to be a constant power output. If there's a car and it keeps going slow and fast, slow and fast, slow and fast, it is going to be a very reliable car because you can't really accelerate. So it's basically useless. But the one on the left is actually useful because since it can carry the boat at a constant speed instead of making the boat going really fast, like 12 miles an hour and then 7 miles an hour. So the one on the left also didn't overheat, making it reliable since it didn't and wouldn't explode. So yes, that was one reason. So now it continues. In Europe, further building off his early discoveries and discoveries of others, Zeno Grami developed the first Grommet machine in 1871, which kind of looked like this. If you took the motor apart, it kind of looked like this, the one he developed in 1871. But when he was presenting this motor to everyone in front of the stage, he accidentally discovered that when he connected two of these devices together, one could be used as a generator, while the other one could be used as the motor. Basically, one could be used as the input or the battery, while the other one could be used as the motor or the output. So he basically discovered batteries. Well, by the 1920s, nations began with developing networks of electric grids. Soon enough, electricity began creeping into everyday life. Gas lanterns were replaced by electric streetlights. Air conditioning could now be, let's just say, affordable. And in 1921, a new concept. This concept is the one right here. There's an air gap in it. Why? In order to reduce friction and increase the amount of air between them. Why? This increases efficiency, meaning there can be a higher power output with a lower power input. Basically, it just made it to not easily overheat. And you could make the same electric motor with cheaper materials instead of really expensive ones. They call this the EMC's PCB stator BLDC motor with air gap field. I don't know why you chose that, but I don't know. This was also used a small air gap between the rotor and stator. Was also found to facilitate the flow of electromagnetic flux in DC machines. Would increase efficiency. Well, wear and tear would be continued to be an issue for these type of motors. Even though there was discovery of the air gap, well, there was still the persistent friction, erosion, and even overheating in high loads. That's why there weren't electric cars back then. But this all changed when someone discovered a 1962 brushless permanent magnet motor, which somehow only became popular 20 years later. Why? Because the materials weren't present at the time, and 20 years later, they had the materials. Since 20 years ago, in 1962, they didn't have the materials and they were real expensive. But in 1982, somehow they were cheaper, so they were able to make it. And this is the motor that we use today. This is the 1962/82 motor we use today. You could say there hasn't been much innovation in 40 years, but innovation is keep going down the drain. Nobody keeps innovating now. So yes, basically, Jerry Genco and Norman Smith patented the motor with a stator on a printed circuit assembly. Basically, this is a logic board, and in each one of those fringes is a tiny bit of electromagnetic strips. And when the electromagnetic strips flow, it just makes an easier electromagnetic field, creating for a smaller, lighter, more effective motor. And this is the type of motor we have in most computers and laptops today. While brushless DC motors today are light years ahead of old trolley motors of the 19th century, but these guys' designs are far from perfection. Since we don't have flying electric cars yet. But in another 50 years, we'll probably have flying planes with electricity, using electricity. And so here's the exploded view of the ECM's patented PCB stator motor design. In 2015, Print Stator was launched to utilize a prototype, a mid-drive solution for electric bike. From discrete inputs, Print Stator automatically generated a unique PCB or GCB. Exploded view or the one we use today in 2015. So it was standard design, completed with associate Gerber file, specifying the detailed build characteristics ubiquitously utilized by the PC manufacturer to print this design. Well, basically, they just invented a way to make these types of DC motors 50% cheaper, or just make them like half the price. With the same quality, you could just make it for half the price. And the ECM PC motor improves on many of the issues that have been afflicted from early electric motors from their invention in 1832, significantly improving on motor reliability, efficiency, and power density, resulting in electric cars. And Elon Musk's Roadster, which can go to 0 to 60 in 2 seconds, I think. So yeah, that's the end. And yes, this is basically the electric motors we use now. There's the end bracket, which is basically the suppressor, the shaft or the rotor inside, the frame, which is the frame to keep it from damaging, the brush assembly, or this is basically the electromagnet. There's the commutator, which is basically the protector case, and then there's the armature, which basically is another protector. And then the bearings to keep friction from overloading and overheating this motor. So that's the end.